Proof by contradiction is often difficult to understand because it feels like we're actually not proving anything at all. Instead, it feels like our proof has been done by some kind of trick and that we haven't learned anything about the mathematics. And so that's true in some ways, but proof by contradiction is completely logically sound and so is always an option for mathematicians. While it's difficult to determine when to use proof by contradiction, there are some times that it makes sense to use proof by contradiction because the negation of our implication has an easy definition and the implication itself does not. For example, rational and irrational numbers. Rational numbers have a clear definition, and irrational numbers are defined as not rational. So if I were asked to prove that a number was rational, then it would be a lot easier to show that the number being rational is impossible. So that gives me that the number must be irrational. It's good to notice that proof by contradiction is only viable if we can transform our application into binary options, like irrational and rational. If we can't, then contradiction does not make sense as a proof option. So let's try this out and see how it actually works. So for example, let's take one of our canonical examples that we want to do. We want to prove, that square root of 2 is irrational. So what I want to see here is that proving that it's irrational would be very difficult, but proving that is rational. So let's suppose that the square root of 2 is rational. Then what I need to do is that I need to show that this is in fact logically impossible. That is that we'll end up with having a statement that we've made be both true and its negation also be true. And once we get there, that must be false. So what we've done is we've logically concluded that something is false. So let's suppose that the square root of 2 is rational. Then we have a definition for that. So root 2 is going to equal, and let's use, we're going to call this n over k for some integers n and k. Now what we're going to do is we're going to make n and k special integers, and let n over k be irreducible. And what that means is that n and k have no common factors. So any fraction can be written as irreducible. What we're going to do is we're going to say let's let that n and k be those values that makes this in fact irreducible. They have no common factors at all. So now the square root of 2 is going to equal n over k. That then implies for us that 2, by squaring both sides, we'll get 2 is going to equal n squared over k squared. So, again, another implication, 2k squared is going to equal n squared. Thus, what that means is that n is even, or n squared is even, which means that n must be even as well. The only way for us to have that n is in fact even is as if, n squared is even, is if we have a factor, of n is 2. If n is odd, what we actually get is that we're going to end up with no factors of 2. We're not going to have 2 as one of the factors inside of n, and so it's impossible to have 2 as a factor of n squared, if you kind of think about it from that perspective. So what this gives me is it gives me that n, we're going to let n equal 2d for some integer d. So we're going to have that 2k squared is going to equal 2d squared, which equals 4d squared. Then what we can do is we can divide here. We can divide both sides by 2, so we're going to end up with k squared is equal to 2d squared. So k is even. What we see there is that k is even because it's going to be 2d squared and d is an integer. So there it is, that k squared, that k is even. Well, we have a problem here. If k, this means, okay, actually, here's our problem. This means that 2 is a factor of k. All right? So, k and n share a factor, share a common factor. And that's where our contradiction comes in. At the very beginning, when we set up our proof, what we stated was that n and k did not share a factor. They were in fact irreducible. And what we've done is we've actually utilized some logic and some algebra to show that, in fact, k and n, if the square root of 2 is rational, okay, then k and n do share a common factor. In fact, they share 2 as the common factor. All right? And that's a problem. Thus, what we can do, just to make this very clear, k and n are share a common factor and do not share a common factor. You see that? That's what we've actually proven, that both a statement and its negation are in fact true. So, square root of 2 cannot be rational. All right? What we've done is we've actually shown that we have what we call sometimes the logical car crash. Okay? Root 2 cannot be rational, thus the square root of 2 is irrational. And that ends our proof. So what we've done here is we've actually said, all right, well, I can't really directly prove that the square root of 2 is irrational, but I can show that the square root of 2 can never be rational, and so consequently must be irrational logically speaking. Okay? And what we want to notice is that having a definition for rationality makes it a lot easier to prove that our function can never have that definition. Okay? And so hence, that's why we utilized contradiction here in this case. And also, the other thing we want to show is how it is that we go about using contradiction. Okay? Using contradiction, this is the basic step for using contradiction. Or these are the basic steps for using contradiction. 1, okay, negate, assume the negation of the conclusion is true. Assume the negation of the conclusion is true given a true hypothesis. Then 2, we will show that the negation of the conclusion gives us a statement that is both true and its negation is true. So what we do is we end up forcing a statement where it's the statement is both true and its negation is true. And that's impossible. That's actually a false statement. So what we've done is we've actually created a logical throughway in which we have two statements, okay, that cannot both be true at the same time. And we've actually stated, all right, if our negation of the conclusion is true, then these two things must be true at the same time. That's impossible. So consequently, we must assume that our assumptions are wrong. Okay? So what that states is that this shows, by contradiction, that the original conclusion was true. And that's how we do proof by contradiction. Okay? Start out, we're going to assume hypotheses are all true, and then we will assume that the conclusion, the negation of the conclusion is true. Then what we'll do is we'll show, utilizing logic and proof, that following that negation being true leads us to two statements that are themselves and their negation are both true at the same time, which is impossible. And then that shows, by contradiction, that the original conclusion was true. And what we want to do at the very end is we want to state, thus, by contradiction, our original conclusion was true. All right, this completes this video.